Hello everyone. In this video I'll be showing you how you can conduct a regression analysis by using Excel. Just for some context, regressions, and more specifically linear regressions, should be conducted only when the response variable, so the dependent variable that you wish to explain, is either continuous or discrete, so quantitative variables, with many outputs or many observations to it. In the example I have here, variable price, as you can see, has many different values that can be taken. That's a perfect variable to use as variable y in a linear regression. The explanatory variables, so the independent variables, those that we treat as x or x1, x2, x3, should be either quantitative, continuous or discrete, doesn't matter, or binary. We have such variables in this file as well. Area is a continuous variable. Rooms, baths are both discrete quantitative variables. Acres is a continuous variable. And metro is a binary variable that simply indicates whether or not a home is close to a metro station, so within, for example, 2 kilometers of a metro station. Fuel and exterior are qualitative variables, and they're not binary in nature either, so those should never be incorporated into a linear regression model unless modifications to these variables are made. That's something that we would see in a future course. So now to perform a linear regression, we're going to use the tools that Excel has for us. In this particular case, we're going to be going to the data menu, and we're going to access the data analysis tool pack, where among the different functions that appear, one is called regression. Okay, so here what matters most is that we insert the appropriate information into the right cells. So the Y range means that we have to insert the variable whose values we're trying to explain. So the dependent variable, in this case, let's say price is the variable we're explaining. As you may have noticed, I included the title when selecting the range of data. As for the variable that we're treating as x, for the sake of this example, I'm going to be using area. So I'm going to choose area and all of the data that comes along with it. Because I included the titles, I'm going to check labels. I'm also going to check residuals, residual plots, and line fit plots, simply to show you what these different options have to offer. And I will click OK. So notice how Excel quickly gave me the result of the regression. So very first thing, at the top left corner, some information is given about the correlation coefficients. So this doesn't look like it's a linear correlation, but it is. It's called multiple R in the regression option of Excel. What this number is, in fact, is the linear correlation coefficient, but in absolute value. So don't trust the sign. 0.6968 happens to be the right sign in this case, because overall, as the area of a home increases, we would expect or we would anticipate that the price of the home would also increase. R square is a measurement of performance attached to regressions. So the closer this number is to 1 means the better the variable called x is a good predictor of variable y. We have an ANOVA table underneath, and I'm going to skip the explanation as to the content of this table because we'll see that in a class setting. And at the very bottom, you will notice information about the coefficients. So the very first one, 167,000, is in fact the estimated intercept or y-intercept. So it is where the linear regression, where the best fit curve, best fit line, would cross the y-axis. The coefficient for area is in fact the slope of the line that we've just created. So for an increase of 1 square foot of the house's dimension, we can predict that on average the house will increase by $129. So essentially it's the slope of the line that we've created. The p-value is provided in this output as well. So when you're going to start discussing hypothesis testing on regression, this p-value will be of great interest to you. Underneath is the residual output. Now, residuals are essentially the errors, because obviously when you have a scatter plot, the best fit line will not necessarily pass through every point. So the predicted price is the price that the regression anticipated for the first entry that you had in your sample. So for example, the first home that appeared in the sample, Excel predicted through regression that it should have had a price of $564,000. Residual is the error that was actually made. So in reality, the house was worth $94,000 less than that. Okay, so the residual output gives you an idea of how precise the regression was in making predictions about the homes that were used to produce the scatter plot in the first place. Sometimes an image is worth more than an explanation. So if I actually take a look at the line fit plot, here's where you'll see what these residuals actually mean. Okay, so the orange dots, which we could convert into a line by using some of the Excel options, is the best fit line, or the predicted price in this case. So this is the line that passes as best as possible through the scatter plot. And you can see that in many cases we've made certain errors. The blue dots are the actual homes that were used to create this linear regression. So very few of the homes are on the line, on the best fit line itself, which is totally normal. Actually, the closer these dots are to the line, the bigger the value of R square would have been. So the correlation would have been stronger, as well as the R square value. You'll notice that Excel did not extend the line beyond any of the points the scatter plot has produced. In other words, the regression line should only be used on the interval of values that you actually see in this graph. So something between, I guess, 600 square feet and maybe 3,800 square feet. Going beyond this range would be an extrapolation. So in other words, we should not be making predictions for the price of homes that are 5,000 square feet, and certainly not for homes that are 0 square feet in area. So we want to stay within the range that is there. Just behind, or also supplied in the Excel output, is the residual plot. So in fact, the residual plot are exactly the same numbers that we saw in the residual calculations on the left, which I'll just remind you of. So what we had here down at the bottom. So the residual plot essentially shows how far off the prediction was for each home in the sample. So dots that are above 0 are dots that were underestimated, represent homes whose prices were underestimated with a regression. Dots that are below 0 are homes whose prices were overestimated. So we have an idea of the dispersion here. What's interesting about the residual plot is that it could be an indicator of whether or not a linear regression is valid. So what we're hoping for is essentially a uniform scattering of the dots above and below, so no particular pattern. This one's not too bad. We've got a few points on the extreme, but you see how there's a cloud of points pretty uniformly scattered around 0. That's a good sign. If I go back to homes, I'll also show you that if you are going to be doing multiple regression, then you can go beyond what we just did in this last example. So I'll return to data analysis, return to regression. I still wish to explain the price of the homes, but in a multiple regression setting, you can actually select all of the data that is either quantitative or binary. So I've chosen area, rooms, baths, acres, and metro. I've selected all of the data for these variables. In the first row I had the labels, so I want to click on that. And maybe just to not have too many things pop up later, I'll just remove the options on the residuals and say OK. Now this is one of the things I find most fascinating about regressions is now, yes, we have the same information at the top. You may have noticed that the R-square has increased, which means that the model that we have just created, which incorporates more than one variable as an explanatory variable, has a higher performance, is a better predictor of price than the other one was. We have the ANOVA table in the middle, and this time we have coefficients for every variable that participated in this regression. So we still have a y-intercept, and we have essentially the slope for every unit increase of area, rooms, bath, and acres. When it comes to metro, we can't really say it's a slope because either we have a home that is near a metro or that isn't. So the coefficient that is there is the multiple for the variable metro. And curiously enough here, the slope is negative, or the coefficient is negative, which would essentially mean that homes that are within 2 kilometers of a metro station actually cost $14,000 less on average. And that would be for all other variables being considered the same or constant. Okay, so $83 increase for every extra square foot of a home, and etc. So multiple regression, if we want to look at the incorporation or the effect of every variable or many variables on variable y. Of course, you don't want to jump to too many conclusions, which is why there are p-values that are also provided. Again, p-values will be discussed in a hypothesis test setting, but just to make a long story short, the p-value is there to tell you whether or not you can actually have confidence, or you can actually truly make speculations about the influence of these variables on price. That's a whole other story, which we'll see at another moment. Thank you very much, and I'll see you soon.